Everybody filed into the room. So I'm pleased to welcome Professor Kun Wang today to give our colloquium seminar. Kun is currently on the faculty at Washington University in St. Louis. Before he gets going, I'll give a brief CV here. So Kun's from China. He attended the China University of Geosciences, where he got his bachelor's degree in 2008. I didn't know this about Kun, but he really wanted to be an astronomer when he was younger. And so he went on to the China Academy of Sciences for astrophysics, but he left there in 2009 before completing a degree because he wanted to pursue a PhD in cosmochemistry at Washington University. So ding ding for cosmochemistry. So he went to WashU in 2013. He went to WashU in 2009, and he finished his PhD there in 2013, working with Fred Mounier, right?
Yes.
Okay. Doing ICP-MS and for cosmochemical applications and geochemical applications. And then in 2014, he left for Harvard to do a postdoc with Stein Jakobsen. He was there through 2016, developing high-precision potassium isotopic measurements for stable isotope fractionation applications. And then he went back to WashU in St. Louis, where he joined the faculty in fall of 2016. And he has a group working on non-traditional isotopic systems. So these are things like copper, iron, zinc, calcium, and others for applications to geochemistry and cosmochemistry using multi-collector ICP-MS. And I think he's going to talk about some of those today. So Kun will be talking to us about a new perspective on the origin of the moon. Kun, welcome.
Thank you, Tom. Thank you for the introduction. Thank you for having me here. It's an honor to give a talk at the LPL, but it's also very intimidating to talk about the origin of the moon, since it's the Lunar and Planet Science Laboratory. So feel free to ask me questions. I won't make this as a discussion rather than just telling you the story. First thing first, I would like to thank all my collaborators and also my funding agency. Without them, all this project won't be able to happen. So thank them very much. And the origin of the moon has been always a fascinating question for human beings. Human beings always be very interested in the moon. And if you remember, just less than a month ago, all over the United States, we are very lucky to see this beautiful lunar eclipse. This is just a picture from Arizona Daily Star newspaper. It's very beautiful blue blood moon. But even though human beings for thousands of years has been fascinated about the moon, but not until the end of 19th centuries, scientists came up a scientific explanation for the origin of the moon. The first most notable theory for the origin of the moon is the fission theory, proposed by George Darwin, the second son of the famous biologist Charles Darwin. So the fission theory is very easy to understand. Conceptually, the early Earth was spinning very fast. Part of the Earth was spun out to form the moon. And the place where the moon used to be is the Pacific Ocean. That's the general idea of the fission theories. But we all know since the end of 19th centuries, there have been more and more theories for origin of the moon. This is the cartoon I like to show my students in my class. There's three general ideas for the origin of the moon before 1970s. The fission theory, the capture theory, the moon was an asteroid, was just flying very close to the gravity field of the Earth, was captured as a satellite of the Earth, or the cold condensation theory, where the Earth and moon condensed from the solar nebula together. And this is the three basic idea for the origin of the moon before 1970s. However, we all know these three theories do not work very well for the origin of the moon. However, these three theories sometimes could actually work for other satellites in our solar system. For example, the fission theory, there have been observed data showing some of the asteroids, some of the irregular asteroids, if they spin very fast, part of it can be spun out to form a two asteroid system. And for Jupiter has many countless moons. Some of them are small asteroids captured by Jupiter. Those big moons of Jupiter are likely formed together with Jupiter. So the fission capture and the condensation theories works for other satellite systems in our solar system, even though they do not work for our moon system. And the reason is our moon is particularly big compared to other satellites of other planets. The mass of angular momentum of the moon is very big compared to other systems. For example, the size of the moon is only 1/80th of the mass of the Earth. If you compare other planet satellite system, usually the ratio is smaller than 1/4000. The angular momentum of the moon, of the orbital movement of the moon, is 4 times of the angular momentum of Earth. If you compare to others planet satellite system, this ratio is smaller than 1%. And the bulk chemistry of the moon is also very different from the bulk chemistry of the Earth. The density of the moon is roughly the half the density of the Earth, means the moon like an iron core. So the density of the moon is very similar to the mantle of the Earth rather than the bulk Earth. Another interesting aspect of the moon is the moon is very depleted in volatiles. Simply by looking at this picture, compared to our beautiful blue marble Earth, there's no water, there's no atmosphere, and all these volatile elements has been depleted. This is one of the constraints for us to understand the origin of the moon. If we look at some data, if we look at the Ku ratio versus the potassium concentration, Ku ratio, potassium is a volatile element, uranium is a refractory element. Ku ratio telling us what is the degree of volatile depletion. The bigger the Ku ratio, the more close to the primitive chondrite. The smaller Ku ratio, the more closer to depleted bodies like the moon. You can tell the chondrite has a much higher Ku ratio. The Earth is depleted in volatiles compared to the chondrite. The moon is even more depleted in terms of Ku ratios compared to Earth. So this is a very strong constraint we have to consider when we test any lunar formation models. Let's go a little bit in details here. Potassium is very typical volatile elements. We call it moderately volatile elements, but potassium is not the only moderately volatile elements. And this figure is a little bit similar to the one I just showed you before, but it's a little bit different. The x-axis showing different chondrite. Ci is the most primitive chondrite in the solar system. Earth and Moon on the other side, they are most volatile depleted bodies. And if you plot their element ratios to titanium and compare to Ci is about 1, and everything else, the different chondrite, they're depleted in volatile elements. So for example, potassium, sodium, zinc, copper, their concentration in those depleted chondrite and the Earth and Moon are several order of magnitude smaller compared to Ci chondrite. And here I just want to say not only potassium, but many moderately volatile elements has been depleted in the moon. And we all know the best way to explain all this observed data for the moon is the giant impact hypothesis. And this just want to show you a quick video to show you the basic idea. We probably already know from high school. The Earth was collided with a Mars-sized planetary tesmos, and the Mars-sized impactor was destroyed entirely, and the moon was formed from the debris and of these impactors. And this giant impact hypothesis was proposed by 2 groups independently in 1970s. I'm very glad today I can meet one of the original proposers of these theories. And since then, the giant hypothesis has become the textbook answers for the origin of the moon. And here are some original modelings for the origin of the moon. You can see people can vary the size of the impactor and the Earth. they can produce a different size of moon, and you can do this kind of exercise to find the best matches with the current moon. And here is just a more modern theoretical calculations. You can see the best size of the impactor will be a Mars-sized impactor, and at different time you see the debris. Eventually, the moon was formed with those debris. However, there's some problem. This giant impact hypothesis has been the textbook answers for the origin of the moon, but with the improvement of analytical precisions of geochemistry, people find one inconsistency in these theories. The problem is here, the standard giant impact hypothesis predicted most of the material, depending the modeling, 60 to 80% of the material of the moon came from the impactors rather than the Earth. But geochemical analysis of the lunar rocks telling us the geochemical composition of the moon in terms of mass-independent isotope compositions are exactly identical to our Earth. This causes trouble because if the moon was formed from the debris of the impactors, and we don't know what's the composition of the impactors, but if you look at the composition variations of different planetary bodies in our solar system, every planetary bodies have their unique composition in terms of mass-independent isotope compositions. So it's unlikely the impactor have the exactly isotopic compositions with the Earth. So unless the moon is from the moon material was from the Earth material, so it's unlikely by chance the moon have the same identical composition to the Earth. So this causes a problem. Again, I'm showing this figure to show you most modeling showing you the moon was accreted from the debris of the impactor rather from the Earth. So it's very difficult to imagine these impactors have the same isotopic compositions with the Earth because through the solar system, each body has very unique isotopic compositions. Let's look at a little bit details in this problem. Here, I'm showing you the oxygen mass-independent isotopic composition. We call it delta 17. It's just an isotopic composition in delta notation. You can see the Earth, the delta 17 is 0. If you measure lunar rocks, different lunar samples, all the lunar samples have about 0 delta 17. It's identical with Earth. But if you compare to Mars, if you can compare to other meteorites like angrite, eucrite, they all have their unique isotopic composition. By the way, this picture is from Professor Asfox's very nice review paper a few years ago. So all this planetary body I'm showing you here, Mars, angrite, eucrite, they have very close isotopic composition to the Earth. There's more meteorite. I'm not showing you in this figure because they're very different from Earth. There's no other planetary bodies have identical isotopic composition to our Earth other than the Moon. So it's very unlikely the impactors have the isotopic composition from the Moon. Oxygen isotope is the most important one. So many groups spending a lot of effort to really improve the analytical precision to test whether this is correct or not. In 2014, actually one group identified a tiny difference between Moon and Earth. You can see the error bar is not much bigger than the differences between Moon and Earth. And in 2016, another group did the same measurement. The 2016 group, they couldn't find any differences. So just want you to know the oxygen isotope between Earth and Moon is still a remaining question whether they're exactly identical or there are small differences. Two different groups gave you different answer. The 2016 ones telling us we still couldn't see the difference, and the 2014 ones can distinguish a little bit difference between Earth and Moon. But if you look at other isotopic compositions, non-mass dependent fractionations, chromium, titanium, you see the Earth and the Moon are identical. But if you look at all the meteorites we have collected representing different asteroids, if you look at Mars, if you look at a lot of different meteorites, they're all very different from Earth and Moon. So Earth and Earth and Moon have identical mass-independent fractionation isotope system in many, many systems, not only oxygen, titanium, and chromium. There's more and more has been discovered. So again, come back to this problem. The Earth and the Moon are identical, but the standard giant impact hypothesis predicting the Moon should like something else, the impactor. Although we don't know the composition of the impactor. So some people say the easiest way to solve this problem is to assume this impactor have the identical isotopic composition with the Earth. So the possible explanation for this problem is the impactor and Earth have the identical composition. So naturally, whether the Moon is from the Earth or from the impactor, it doesn't matter anymore because they do have the identical composition. However, we don't have any way to tell what is the isotopic composition of this impactor because it has been destroyed. But just by compared to meteorite, it's unlikely these two bodies have the same isotopic composition. But this is still one possibility. We don't have a way to really exclude these possibilities, but the chance, the likelihood, probably pretty small, based on the variations of those isotopic systems within the solar system. The second possible explanation is no matter whether the impact on the Earth the same or not, after the giant impact, there is a very thin silicate vapor around both the Earth and the lunar forming disk. So the lunar forming disk is mostly from the impactor. The Earth is a different composition. But through exchange of this vapor atmosphere, you could homogenize the composition. So even though you have a different impactor composition, you can mix the Earth and the impactor, and they end up, the current Earth, the current Moon have the same isotopic composition. So no matter whether the proto-Earth and the impactor are different or not. So this is the second explanation. The problem with the second explanation is the time scale of this silicate vapor atmosphere is do not have enough time to exchange the material of Earth and the lunar disk entirely. So you don't have enough mass. The atmosphere is very thin. You don't have enough time, enough mass to exchange these two huge bodies to mix the isotopic compositions. So this is very unlikely you can mix the disk and the Earth. And the third explanation is maybe the standard giant impact hypothesis has a problem. Maybe we should look beyond the standard giant impact hypothesis, come up some other models for other scenarios of giant impacts. Maybe a more energetic giant impact. You not only break down the whole impactors, you also destruct the whole Earth. You not only melt the Earth, you actually vaporize at least the upper mantle of the Earth. So as shown in this new paper published last year by Locke and Stewart, you could have a very energetic impact, and you actually vaporize the upper mantle of the Earth and form this very gigantic, supercritical bulk silicate Earth vapor fluid structure. And they even came up a very interesting name for it. And this structure is very different from either a pure planet or a planet and a disk system as predicted by the standard giant impact hypothesis. If you have a much more energetic impact, whether you have a bigger impactor or you have a higher velocity, higher impact, you can do this by different way, but the end product is you vaporize the upper mantle of the Earth. This way, you can entirely mix the impactor and the Earth. No matter what's the previous composition of the Earth and impactor, you entirely vaporize it, and the Moon was formed as a condensate of this vapor fluid. So this way, you can have the same isotopic composition between Earth and the Moon. And this has been proposed as a hypothesis. We have to use real measurement to approve, to confirm, to test this model. And here comes to our group. Our group was focusing on study volatile elements. During a condensation evaporation processes, those moderately volatile elements, such as potassium, would produce isotopic fractionation. So we compared the standard giant impact models and this new bauxite earth vapor models. We predicted the bauxite earth vapor model will produce a moon, have a higher potassium isotope composition than the potassium isotope composition of the Earth. And we want to measure the potassium isotope composition of the moon and Earth and compare them to test different isotopic models. The reason why the moon have a higher isotopic composition than Earth because the moon was formed as a condensate of this vapor. By the principle of isotopic fractionation, the condensate should have a higher isotopic composition than the vapor. The vapor will fall back to the Earth to form our current Earth. So with this question in mind, we studied high precision isotopic composition of the Earth and the Moon. And here's our data. The Earth points are shown here. All these points representing different igneous rocks, from basalt to granite. So it's a variety of Earth rock. You can see the variation of potassium isotope are very small. And here are showing all the lunar samples, including Apollo samples, basalt, breccia, a variety of type of lithologies. Also, we recently measured 2 lunar meteorite. Lunar meteorite representing a different collection of lunar samples other than the 6 Apollo return samples. We can see they all clearly distinguished from the Earth composition. And the chondrite to compare with, chondrite, they're very similar to the Earth. We don't have enough resolution to distinguish between Earth and chondrite. But the major discoveries in this isotope study is we found a significant difference between Earth and Moon in terms of potassium isotopes. And this agrees with our prediction if the Moon was formed as a condensate of the bauxite Earth vapor.
Is there any significance to the Y variation, or was that just convenience of plotting?
Convenient plotting, no. And just want to give you a little bit details on why people haven't done this before and what we have done to make this happen. Before 2016, before we published the method of high precision potassium isotopes, the precision of potassium isotopes is very big. So the error bar is several per mil. This potassium isotopes, the variation is several per mil. If you measure the same sample, they varies by 1 per mil. The same sample, if you measure them multiple times, they give you a different number because the analytical precision is not very good. But after 2016, after we're using this new method, we can really we improve the isotopic precision by an order of magnitude. You see, if we measure the same sample, they all get the same number. So this way, we can see the difference between Earth and Moon. Previously, people did look at potassium isotope between Earth and Moon, but because the error bar is 1 per mil. But in reality, the difference between Earth and Moon is only 0.4, 0.5 per mil. So if you have 1 per mil error bar, you don't see their difference. Only when we drop the error bar below 0.05, we can start to see clearly the difference between Earth and Moon. And not only by qualitatively, we can, using the potassium isotopes, we can test the different moon forming scenario. We can also learn more the conditions forming the moon. So if we look a little bit details of the isotopic data, here we're just plotting the average potassium isotopic composition of the Earth. Here's the average isotopic composition of the Moon, is the same with the data I showed you earlier. And I also plotted the Ku ratio of Earth and Moon. Again, Ku ratio telling you the volatile depletion degrees. Relative to the Earth, the Moon is depleted in volatiles. So the Ku ratio is 20% of the Ku ratio of the Earth. And we can explain, we can using the difference between Earth and Moon to constrain what's the temperature and the pressure of the Moon formation. Because we can do some simple Rayleigh fractionation modeling, we can come up a Rayleigh fractionation factor, and this factor will be affected by the temperature and pressure. Isotopic fractionation between two different systems can be decided by the temperature and pressure. So this number here is simply fitting the data points, but we're trying to use this number to constrain the temperature and pressure. To do that, we have to do laboratory experiments to really calibrate what is the Rayleigh fractionation factor at different temperature, different pressure. There are very few data so far to do this kind of experiments. That's because clearly before 2016, potassium isotope was not very useful. There were not any variations between any system, so there are very few interest doing this kind of experiments. But very lucky I can find two experimental data calibrated between the isotopic fractionation factor and the amount of isotopic amount of potassium depletion. So just give you a little bit detail. You don't have to know these numbers. But if we have a Rayleigh fractionation at a vacuum, 0 pressure, we should have this number as 0.97. But we found the number we fitted from the moon data is much higher than 0.97. So this can be explained by high pressure fractionation. Here just showing you the different pressure. There are different experiments at different pressure. If you have higher pressure, you will have higher alpha, the Rayleigh fractionation factor. This is just a little bit detail to explain how did we really constrain the pressure and temperature of the lunar formation. Again, and this is the pressure versus the Rayleigh fractionation factor, the alpha I showed you earlier. The number we inferred from our lunar value is about 0.999. It's very close to 0, close to 1. And the red dots are experimental data from the figure I just showed you earlier. We can see there's a clearly pressure effect affecting this alpha Rayleigh fractionation factor. So we can using this measured Rayleigh fractionation factor to infer the pressure of the lunar formation is bigger than 10 bar. Again, there are very few potassium isotope real measurement. The red dots you can see it's very limited. So in the future we can better constrain this, but this is the best we can do with current existing laboratory experiments. In the future we'll definitely improve this. So we can infer the moon was formed as a condensate in a very high pressure vapor. And this agrees very well with the model I showed you earlier. More energetic impact could create a bulk silicate earth, very thick vapor, and then the moon was condensed from that. Other than the potassium isotope evidence, we also have evidence from simply the elemental compositions. So here I'm showing you the moon composition, the bulk moon composition inferred from many measurements versus bulk silicate earth composition. One means there's no difference between earth and moon in terms of elemental composition. If below that, it means the moon is depleted in volatiles compared to earth. You can see the range of the real moon is in the purple bluish area. All this colored line are theoretical calculation. If you simply condense a condensate from a bulk silicate earth vapor, if you do a thermodynamic calculation, what kind of elements composition you can predict. At different temperature, different pressure, you get different moon. So the best fit for the moon, current moon composition is about 20 bar 3000 K, more than 3000 K. So this also agree with the pressure we inferred from the potassium isotope, as I just showed you using the alpha, the Rayleigh fractionation factor. And here is just showing you the thermodynamic calculation. We can assume a bulk silicate earth vapor. If we drop the temperature at different pressure, we can form different melt phase, different crystal phase. If we assume the moon was condensed as a melt, we can predict the isotopic, will predict the elemental composition of it. This is just explanation for the figure I just showed you earlier. We can do this theoretically using thermodynamic constraints. And here just showing you the potassium is a volatile element. At high temperature, most potassium in the vapor, but only you reach a lower temperature, the potassium will condense in the melt, and the moon was collecting all this condensed material. If you add up them together, you can form the moon. And the composition, isotopic composition, and the elemental composition, they all agree very well with the current observation of the moon. So the potassium isotope of the moon measured in Apollo samples and lunar meteorite agree very well with this prediction if the moon was formed from the more energetic giant impact hypothesis. However, after we published this paper to explain, to propose the moon was formed as a condensate of the bauxic earth vapor, there's a few other opinions. There's some alternative explanations for the potassium isotope fractionation. Here just showing you what's the possible way to fractionate potassium isotope. The first one is nebular processes. We exclude that because we tie the moon with the Earth very, very closely. So we assume the moon should be the same with the Earth before the moon formation. So we don't need to consider any nebular processes. And for planetary processes, other than the accretion events such as the giant impact, we could also have magma ocean degassing or local lava flow or eruption outgassing to fractionate potassium isotope. And here, just some criticism I got. Some people propose alternatively potassium isotope could be fractionated during magma ocean degassing. You can lose potassium as vapor. You can also fractionate potassium isotopes. So some people are arguing maybe the potassium isotope fractionation you observe has nothing to do with the accretion event, the giant impact, but caused by other processes. But my answer here is no, because potassium is not very volatile. I'm going to show you more evidence why I assume that's the case. Potassium is very volatile, but not as volatile as a degree to be fractionated during magma ocean degassing or lava flow eruption outgassing. For other volatile elements such as zinc, copper, and chlorine, there are also volatile elements. Many people has measured zinc copper isotope of the moon. They found the moon is enriched in heavy isotopes, but they've explained that as the magma ocean degassing, and they argue why didn't potassium isotope was just simply the result of magma ocean degassing. Here are some explanation why I don't think that's the case. To test that, we can look at some terrestrial analogs. The number one terrestrial analog is tektite. Tektite are natural glass material formed by impact on Earth. If you have a big impact on Earth, you will melt the Earth surface material. You have those splash material falls on other places on Earth. They form this kind of glassy tektite. They are not meteorite. They are just melted Earth surface material but caused by impact. Many people compare the tektite to the moon, to the moon forming processes. There are some similarities. That's why we want to look at the tektite. We want to check whether the potassium isotope of tektite similar to the Earth surface material or not, to check whether a small scale impact could produce a potassium isotope fractionation. And the reason we're doing that because zinc isotope has a huge fractionation in tektite. You can see the green bar here is the Earth composition. The moon is a little bit heavier compared to the compared to the Earth composition. The tektite is also higher compared to the Earth material. Remember, tektite was formed from the Earth material, and you can tell the moon and tektite have very similar zinc isotope composition. And if you look at copper isotope composition, the moon is slightly heavier than Earth. the tektite is much heavier than Earth. And many people, so we can tell copper zinc isotope can be easily fractionated during a smaller Earth impact. Even a smaller scale impact on Earth, you can generate a large volatile depletion and fractionation on the isotopes. But if you look at potassium isotope compositions, you can tell the tektite is about scattered around the Earth value. The Moon is clearly separated from tektite and Earth. The point of this study is to show you a smaller scale impact, a very small impact. You couldn't fractionate potassium isotopes. And we also did some calculations. If you heat a terrestrial surface material to a few thousand degrees or at different pressure, you can easily volatile zinc and copper. You can easily lose them. But you are very difficult to lose potassium until you reach a much higher temperature. So the point of this is to show you the Moon, the potassium isotope fractionation measured in the Moon is very difficult to explain by a very small scale impact. It has to be a very energetic impact in order to lose potassium, because to compare with copper and zinc isotope, they're similar in terms of properties. They can easily fractionate it during a smaller scale, even a surface impacts. And here's just a little bit more detail to show you the tektite versus the Earth surface material. The Cl represent Chinese loess. The Chinese loess is a good source material for tektite. You can tell potassium do not deplete compared to Earth, but copper and zinc, they're very easy to be depleted. And if you look at lunar data, copper and zinc, they're very easy to be volatiles. The isotope composition of copper and zinc isotope in the Moon can be fractionated by many processes rather than the giant impact. But on contrast, potassium isotopes are very robust. It's very difficult to fractionate potassium isotope other than a very energetic impact. So again, just want to show you this slide again. Potassium isotope can be only fractionated during a large giant impact. You cannot fractionate potassium isotopes during a magma ocean degassing or even localized outgassing events. Some people still have a little bit concern whether the only way to fractionate potassium isotopes is through an energetic giant impact. So we also studied a second terrestrial analog, which Trinity rock. Trinity rock, their product after nuclear explosion test, is showing you after nuclear explosion test, the desert sand will be melted, vaporized, and recondensed for this kind of glassy green color minerals, glass tektites. So just want to show you a quick video showing you this process and why do we use this to compare to the formation.
At 5:30 a.m., July 16, 1945, the world entered the atomic age with an intense flash, a sudden wave of heat, followed by a tremendous shock wave. The ball of fire extended 40,000 feet. The bomb packed a punch equivalent to 20,000 tons of TNT, the high end of most of the scientists' predictions, completely vaporizing the steel tower and heating the desert sand into glass for a radius of 800 yards.
So you can tell the most energetic experiments human beings can do on Earth is this kind of nuclear explosion test. So we want to study the potassium isotope fractionation during this process and compare to the data we observed from the Moon. And here are the results from the tektite. And we have samples from the samples we have closest to the impact is 10 meters from the center of this nuclear explosion. And we also have samples from 100 meters, and we also have some samples spread more than 100 meters away from the center of the nuclear explosion. And the y-axis showing you the potassium isotopes composition. The green bar, the blue bar showing you the bauxitic earth composition. You can tell only the 10-meter sample are slightly heavier than the earth. It's only 0.1 or less than 0.2 per mil heavier than the earth composition, the source rock, the local sand. And the reason we're doing like leaching experiments is just because the Trinity rock has been contaminated. There's a lot of surface contamination. We really want to know what's the original composition. So we did a lot of leaching experiments. We can tell only the 10-meter ones have a slight potassium isotope fractionation. The moon is way here, above, around zero, above zero. So the point of this study is to see whether the biggest, most energetic experiments on Earth could fractionate potassium isotope. The answer is no. You can only fractionate potassium isotope a little bit, and you cannot even compare to the data we measured from the moon. So the conclusion, again, this is just comparing potassium isotope and the zinc isotope. And zinc isotope, if you measure the same Trinity rock, you have a huge, this blue bar is the zinc composition of the bulk earth. You can easily fractionate the zinc isotope, but the orange bar is the potassium isotope bulk earth. You can only fractionate the 10-meter ones, but not those 100-meter ones. But even that, you only have a tiny fractionation compared to the moon. The moon is way up here. It's very difficult to fractionate potassium isotope. So the only way currently we can explain the enriched heavier isotope as potassium isotope composition of the moon is through a very energetic giant impact hypothesis. So the conclusion here is we measured potassium isotope composition of the moon and the Earth in high precision. We found for the first time there's a 0.4 per mil fractionation between Earth and moon. And the best and the only currently available explanation for this fractionation between Earth and moon is through this high energetic giant impact, and the moon was formed by condensation from a bauxitic earth vapor at high pressure and high temperature. And thank you. I'd like to take any questions.
Okay, questions for
At the 2014 London meeting, there was a lot of emphasis on trying different impacts, different sizes of impactors, different velocities. And I guess my question is, why would you say they didn't ever get into the range of impact size that you're talking about? And second question is, how big an impactor are you talking about?
The impact we needed to really vaporize the Earth has to be an order of magnitude higher than the standard giant impact. So yes, I agree. 2014, there's a meeting about the origin of the moon, trying to solve this the problem I presented to you in the very beginning. You have to find another giant impact hypothesis in order to fix this problem. So the traditional one has problem. So many groups are trying different way. Today I just presented you one solution for this problem. There are other people, other groups are trying to vary the size of the impact. Some group proposed 2 Earth-size impactor. They impact with each other. They could mix a material. The point of this talk to say we have to be open-minded. There could be more than one solution. I'm just proposing one. At least there's one way to solve the initial problem, but there could be multiple solutions to this question. You could vary even for this more energetic impact. We don't really know the size of the impactor. You could vary the size of the impactor, but you have to increase the impact velocity. either way, you have to make the impact have higher energy. So you can bigger impact, a bigger size impactor, higher velocity. So there are multiple ways to do that. But the result is you vaporize the Earth, and you can mix everything together, and also the isotope, the condensate of the isotope matches the current observation.
Does that take you into a regime, this enormous impact, where you're beginning to interact with the mantle of the Earth? The iron core. And therefore, you kind of lose the advantage of the giant impact model because you're getting too much iron into the moon?
In this particular model, I cited from 2017, they don't, even the lower mantle is intact. It's a gradient. The upper mantle is vaporized, and the closer to the core, the pressure is higher and higher. Even the lower mantle, it's just melted. So the core is still solid. So they have in the model, they have a clear, it's a gradients, pressure, temperature gradients in this structure. And this donut-shaped structure.
Other questions for Kuhn? Is that Adam back there?
The question of mixing. So does this huge cloud, porous material have to be extremely well mixed? Maybe you can comment on the relation of that issue to the earlier issue from 10 years ago about considering the possibility of the traditional scenario with very well mixed bits. How easy is it to ensure that isotope ratios are extremely well mixed with porous, or do you need that?
In their model, so the whole structure is very unstable. There's a lot of turbulence, a lot of mixing going on. So it's a very unstable structure. It only lasts for very short of time. I don't remember exact number in my mind. So in their model, everything's well mixed for the upper mantle, lower mantle. But how deep you go, really depending on the parameter you put. You can, if you want, you can even make the core melted, then that's a problem. So they don't want to go that far. So the entire upper mantle is entirely mixed.
Well, I wasn't referring to the upper mantle. I was referring to this huge torus of material from which the moon is condensing in your scenario, if I understood it right. Does that torus of gas need to be well mixed?
It needs to be well mixed.
Is that easy to do?
In their model, I think they assume that they're well mixed, but in terms of physical modeling, I'm not sure whether people can check their modeling or not. So I don't know the answer exactly.
When you mix material, you also, there's a tendency to transport angular momentum. There's all sorts of fluid dynamics issues that can come up.
I think they considered all of that, but you have to refer you to their paper to see the details.
So I have a question for you, Kuhn. So you talked about potassium, obviously, but what about other light isotopes or volatile isotopes? Would you expect confirmation or consistency if you were to do measurements in other systems?
As I showed you, we compared to zinc and copper because they're very similar in terms of geochemical and cosmochemistry features. So it turns out potassium is not as volatile as them. If you have a very volatile element, you get to vaporize very easily during magma ocean. So the isotope composition you measure right now can be imprinted by several processes. But so far for potassium is kind of unique. It's not that volatile, but it's not that refractory. If it's too refractory, you don't see difference because you condense, it will go to the condense right away. So for the moderately volatile, you only condense partially. You still have some in the vapor, so you create fractionation. Right. So potassium is like the sweet spot. Okay. So it's not too volatile. Otherwise, you can have other process to fractionate it again and again. So you don't really know which time you really fractionate it or not.
I was thinking about things like chlorine. Is that too volatile?
Chlorine,
yeah.
Chlorine is too volatile.
Okay.
We compare chlorine to
sodium.
Sodium does not have the sodium could be very similar. The problem with sodium only has one isotope, so we couldn't use isotopic measurement to do anything with it.
Yeah, we could go phosphorus, right? We could keep going, right?
Yes.
That only has one isotope.
Phosphorus is too siderophile. And potassium is lithophile, so it goes with the earth mantle. Yeah, yes, there are other constraints. So currently there's no good. Cadmium is too volatile, so and very low abundance, so it's very difficult to do measurements. So there's not another good current candidates to check.
Yeah.
Another problem with the giant impact model at that London conference, the emphasis was on distant impactors. I think partly because of the interest in the Grand TAC model and so forth. So people were talking about impactors from the outer solar system, which horribly aggravates the whole isotope crisis problem because the isotopes are so different. And it always seemed to me that one solution to that is to come back to local objects. And we know that there were parent bodies in the inner solar system with very similar isotope composition to Earth, namely the instantite chondrites. And so my question here would be, if whatever you want to do with your impactor to make it more energetic, if you make that impactor an instantite chondrite body, does that help in the overall problem, since you start out with isotope ratios that are virtually the same as the Earth?
If we know the impactor is identical to the Earth, we don't need another model because standard model will work, because if the impactor is similar to Earth,
well, don't you still need to separate out the potassium isotopes the way you talked about?
For the model, you mix everything. We don't consider the precondition, the pre-Earth, the impactor, whether they're same or not, doesn't matter anymore. The structure, the vapor of the whole Earth will mix everything. So whether it's same or not, we couldn't tell. So that would be false in this explanation. So if the impactor is same with Earth, we don't have to have a new model. But we really don't have reason to believe it's the same. It could be the same. The problem is we couldn't exclude that.
I guess what I'm hearing is that if we start with an instantite body and we make it very energetic, both of those directions would help solve the problem.
But yes, the two way to solve the problem, but you can combine them together. Yeah, then it's the same.
Any other questions for Kuhn? Okay, if not, we're going to dinner at 6:30 at Downtown Kitchen, but otherwise, let's thank our speaker.